Hello, everyone. My name is Liming Shi, come from Aalborg University. Today, I'm going to present an accepted paper in ICASSP 2020 about sound zone control. The paper's title is a fast reduced rank sound zone control algorithm using the conjugate gradient method. In this talk, I will go through the background, the subspace construction, the proposed conjugate gradient algorithm for sound zones, simulations, and the conclusions. First, let's go to the background. In this figure, it shows a system geometry of the sound zones. As you can see from the plot, that the input signal xn is first put into a control filter called Qn, and then the filter signal will be fed into the loudspeaker to be played back. And the playback signal will go through the room impulse response called Hn, and then go to different zones. Usually, in sound zone control, there are two zones defined called bright zone and dark zone. In the bright zone, it's supposed to hear the sound signal clearly, and in the dark zone, it's expected to be silent. As you can see from the previous plot, the sound zone control is in fact a filter design problem. The reproduced sound signal can be written as a linear convolution between the input signal xn, the control filter qn, and the room impulse response hn. And our target is to design this qn to have a bright zone and dark zone. The L is the loudspeaker number. There are some traditional approaches for sound zone generations. The first, the state-of-art approach, one of the state-of-art approach is the variable span trade-off filter, which is based on the generalized eigenvalue decomposition. The best approach has the trade-off property between the acoustic contrast and the signal distortion, and it consists the traditional ACC and pressure matching approach as special cases. However, the disadvantage of this approach is that the mu is not a physical meaningful parameter. Also, it's computational complex to solve the generalized eigenvalue problem for large matrix. There are some performance metrics defined in sound zone control. One is called dark zone energy. The second one is called the signal distortion. It measures the difference between the desired signal and the reproduced sound signal. The third one is called acoustic contrast. It's defined as the acoustic energy ratio between the signal in the bright zone and the signal in the dark zone. The fourth one is target to interference ratio. It's defined as the acoustic energy ratio between the desired signal in the bright zone over the interference signal in the same zone. There are some traditional there are many optimization criterions in sound zone control. One of the criterion is to minimize the signal distortion with the constraint on the dark zone energy. Before we go step into the detail of the proposed algorithm, that we first introduced a subspace construction approach called the Krylov subspace. The Krylov subspace is defined in equation 6, and as you can see, it had the information of the small r and the capital R. The capital R is usually the autocorrelation matrix. The small r is usually called the cross-correlation vector. The cross-correlation vector contains the information of the desired signal and the autocorrelation matrix contains the information of the input signal only. So the difference between the Krylov subspace and the subspace built from the generalized eigenvalue decomposition is that the Krylov subspace use the information of the small r, that is the desired signal statistics. In this paper, that we are going to use the conjugate gradient algorithm. The reason for using this algorithm is that the search directions in the conjugate gradient algorithm form the Krylov subspace. The second reason is that the directions are mutually r orthogonal. The third reason is that it's computational cheaper. The fourth one is that the small r is used when constructing the subspace. That is, we utilize the desired signal statistics. Now we are ready to go to the detail of the proposed algorithm. We constrain our control filter to be a linear combination of different bases. And then we plug the equation Q equal to UZ into the optimization problem 5. Then we can obtain the an equivalent equation 7. And we use the search direction in the conjugate gradient method to form the basis matrix. And after some mathematical calculations and EV eigenvalue decomposition, we can obtain the optimal control filter at equation 13. The major difference between the equation 13 and the variable span trade-off filter is that the subspace constructed was using the conjugate gradient method in the current approach compared to the GVD-based approach in variable span trade-off filter. Also, if we plug equation 13 into the constraint, and we can obtain the optimal mu, that is the optimization parameter in equation 14. And the Newton search can be used to find the solution. Next, we show the simulation results. And in this figure, it shows a sound zone generation system setup. As you can see, that 8 loudspeakers are used in the setup, and the 25 control points are used for each of the zones. The sampling frequency is set to 8 kHz. The room impulse response is set to 0.2 seconds. The length of control filter is set to 15 milliseconds. And 6 seconds long speech signals are used as the input signal. In the first experiments, we show the results of the acoustic contrast, signal distortion, and target to interference ratio over the power ratio. As you can see, that the ACC approach has the largest acoustic contrast. The pressure matching approach has a low signal distortion. Well, the proposed RCG approach and the VEST approach has the trade-off property between acoustic contrast and signal distortion. And when the acoustic contrast of the proposed algorithm is set to the same as the VEST approach, that the signal distortion of the proposed is around 4 to 5 dB lower than the VEST approach. When the signal distortion of the proposed approach is set to the same as the pressure matching approach, that the acoustic contrast of the proposed approach is around 4 to 5 dB lower than the pressure matching approach. Next, we also plot the results of acoustic contrast, signal distortion, and target to interference ratio over the number of iterations, or the subspace dimension. As you can see, at around 100, the proposed RRCG approach start to converge. And around 200, the proposed RCG, the acoustic contrast of proposed RCG approach is around the same as the variable span trade-off filter. However, the proposed approach is around 4 to 5 dB lower in terms of the signal distortion than the variable span trade-off filter. However, the good thing about the proposed approach is that the proposed RCG approach has a low computational complexity. As you can see from this plot, when the data dimension is 4,800, that the computational time of the proposed RCG is around 7 times faster than the variable span trade-off filter. So in conclusion, that a fast reduced rank sound zone control approach using the conjugate gradient method is proposed. The conjugate gradient method is applied to form the basis for the solution space due to its low computational complexity compared with the GVD. Around 4 to 5 dB lower performance than traditional GVD-based sound zone control approach in terms of acoustic contrast and signal distortion. However, the proposed approach has a much lower computational complexity than the GVD-based approach. So therefore, it's more suitable for practical use than the GVD-based approach. Thank you all for watching, and I wish you a good day.